All right, so we have water in a piston cylinder assembly. Initially has a quality of 0.65 and a temperature of 99.63 degrees Celsius. Undergoes a constant pressure to a final temperature of 200 degrees Celsius. And it tells us that 400 kilojoules of work is done by the water, by the system, on the surroundings due to expansion. That 400 kilojoules is a positive number. If it had told us that 400 kilojoules of work is done on the water, on the system, it would be a negative 400 kilojoules, but it's not. It's a positive 400 kilojoules. And then we want to find the mass of the water, the heat transferred in kilojoules per kilogram, and we want to draw that process on a TV diagram. So let's put a little place for my assumptions, and now I need to get my mass. So what I'm going to do is I'm going to use the big W term and then an equation for the little w, which I'm going to derive. So my big W is 400 kilojoules. My little w would be due to boundary work. Of course, I need to assume if I'm going to use this equation right here, I've got to use the assumption that it's a quasi-equilibrium process, that expansion process happens very slowly. The pressure is the same. That comes out of the integral, but you might want to say, well, what's the pressure? That's not given. I'm given a temperature. Well, remember those saturated water tables. You know it's saturated at state 1 because you're given a quality. Those saturated tables, you got one A2 and one that's A3. So one of them is organized by temperature, one of them is organized by pressure. And normally if you were given a temperature, you would go to the one that's organized by temperature, but it's not a nice, neat value. So if you go to those tables that are organized by temperature, you'd have to interpolate between two values to get the corresponding saturation pressure. Or you can kind of look at those table A3 just to check and see if it's on there, because boy, that 99.63 is a pretty oddly specific number. And it looks like that is the saturation temperature at 1 bar. So you could also say at 1 bar, your saturation temperature is 99.63, or you could say at 99.63, your saturation pressure is 1 bar. So 1 bar or 100 kilopascals, that's what I'm going to plug in there. And I can calculate my mass of 3.74 kilograms. Next, I need to find the heat transfer. So I'm going to apply my first law. I'm going to get rid of that kinetic and potential energy changes from 1 to 2. And then I'm going to kind of put things in terms of little q. So let's look at each one of those terms. The m times little q, that would be kilograms times kilojoules per kilograms. So that's my big Q. And then the big W, that's given to me, it's the 400 kilojoules. And then delta big U is equal to m delta little u. So I just need to solve for little q. And I know the big W, I know the mass, I just need to look up U1 and U2. So for state 1, I know I'm saturated, and I'm going to go to those same tables that I got the saturation pressure out of. So here I'm going to use, I'm going to use for state 1, I'm going to use the U sub F and U sub G values that are at that 1 bar, plug and chug with the quality, get my U1. And at U2, it turns out that at 100 kilopascals or 1 bar and 200 degrees Celsius, you're superheated. So just go to those superheated tables and pull off the corresponding U2 value and plug it in, and you get 776 kilojoules per kilogram for your heat transfer. Then you need to draw it on a TV diagram. So you'll see that the little dotted line, that's a line of constant pressure, just kind of an outline, because I know this is a constant pressure process. So the bold line, the one that's drawn in red or as a solid line from 1 to 2, that's my actual process. So you don't have to put that little dotted line, but if you want to, just make sure that you indicate somehow that it's really obvious where the line is from state 1 to state 2, and I think it's pretty obvious here. So I've got all the temperatures labeled. I've got my process path clearly drawn along a line of constant pressure, and I think that's it. I know T1, I know T2. Let's see, V1 and V2, I do need to, I can calculate that V1, which I haven't shown here, but you can calculate that. Actually we did. We pulled that off for our work. So V1 is found in your saturated tables, or calculated using the values in your saturated tables, the V sub F and the V sub G values using that quality. And then your specific volume would be found in your superheated tables. So, all right, well, I hope that was helpful. Thank you so much for watching, and let me know if you have any questions.